Look at this video for the setup that I will be using in this. There is a link in the text for this video. In this video I look at the degradation of the signal-to-noise ratio when a strong signal is present outside the desired frequency range. And I will look at different frequency separations and compare with what we have on the AirSpy HF+ to what we have on the Perseus. The first case is a frequency separation of 2 kHz. This is the signal, and here is the interference. I have now a narrow filter on the desired frequency, and you can see Perseus is pretty reliable, and it tells me the level is minus 118 dBm. And that is the level of this reference signals as you have seen in previous videos. I now set the normal bandwidth 2 kHz, and then I get also some noise into the measurement. So it shows minus 116, but the signal is minus 118, and those additional 2 dB is due to the noise. I will now increase the strong signals 2 kHz below until I see a degradation. And for that I enable the audio, and then I use this instance of Linrod to measure the signal-to-noise ratio. And you can see it's here, about plus 0.5 dB. And I turn on that interference until I see a loss in performance. Oops. Here I have a loss of about 3 decibels. But as you can see here, the noise floor isn't quite flat. So this is probably partly due to the sideband noise of the signal generator, combined with the fact that the notch isn't sufficiently deep for this experiment. But that is for the Perseus. I can check what is the level of the interference. And Perseus tells me it is minus 12 dBm. Now I move the signal to the other side of the interference to the other side of the desired frequency. So I step 4 kHz upwards. Once and twice. And now I am on the other side, and I have no degradation. I have to increase the level. The notch filter is not quite symmetric. So, something like this. Now I have lost about 3 dB. And I check what is the level here. And I read minus 14 dBm. Now I have enabled the STR-Sharp 1633, which has the 1.2 firmware. And I bring up the signal level until I see a 3 dB loss of performance here. And it's now at 0, so I need -3. This is -2 dB. So So here we are, something like this. And then I use the passives to look at what is the signal level. Here is the mouse. And I read -22 dBm. And I shift the signal to the other side of the passband. Sorry. Like that. And this isn't so good. Well, here we have a 3 dB loss again, and the passive tells me that the level is -20 dBm. So I disable this one and start this one. This is the unit without the pre-selector. And I need a 3 dB degradation here also. And this is about the level. And on the passives I read -20. And I go to the other side. And I want again this 3 dB degradation. And, well, let's make it here. Because it became much worse when I went up 1 dB. And the level is minus 21. Minus 21 dBm here. So now it's tuned correctly again, and I increase the lead signal level of the 2 kHz offset signal, and until I see a 3 dB degradation here, and 1 more dB is clearly too much, so I stay here and look for the level. It says minus 21 dBm. Not so surprising. The HF plus units are very similar. Minus 21. Now I am on the other side, and the Perceus tells me that the level here is minus 20.3. That's minus 20. Now the separation is 5 kHz. Signal is 5 kHz below, and I'm checking the Perceus. Now the interferer is weak, and I put it on. And this is more like 4 decibels. So I back off by 1 dB. And now it's about 3 dB degradation. And the signal level for that is minus 7 dBm, so it's really strong now. Here is now the AirSpy HF Plus with the 1633 version, and I bring up the signal, and you can see the loss is 3 decibels now. And the level I can read in the Perceus is minus 20 dBm. Here I have a 3 dB loss, and that is at minus 17 dBm. And I must say I had to remove the signal, switch on and off the HF-AGC, because something went wrong with this memory effect when the very strong signal was present while I was testing the Perceus. Now I'm running the unit with the preselector. I haven't changed the signal level, and I see I have about 1.5 dB more degradation. So, just an experiment. I switch off the strong signal, or I make it really weak, enable the AGC, disable the AGC, and put back the signal. And there was no change. So I have to reduce a little. Like this, perhaps. So I switch it off again. To verify that this was a 3 dB degradation. And the level for that is minus 19 dBm. The offset is now 20 kHz. 20 kHz below the desired frequency. And I'm listening to the Perceus, and bring up the signal level until I see 3 dB degradation. It's about here. And Perseus tells me the ADC is clipping. So I have compression because of clipping. This is unacceptable. So 1 dB less. This will be the maximum for the Perseus. And note that the signal to noise loss is about 1 dB only. And the level on the strong signal then is -4 dBm. That's the clipping level of the Perseus. I'm running now the 1633 version of the SDR Sharp with the 1.2 firmware, and I have set the level for a 3 dB loss of signal to noise ratio. I remove the strong signals, so you can see that. About 3 dB. And the signal level for that, I have to restore it, of course. Then I can look on the Perseus, and I find that the level is -24 dBm. Not very surprising. Without changing the level, I still have 3 dB degradation on this unit. And I switch that off, and I switch this one on. And then I remove the strong signal. And we still have about 3 dB. So they all are at -24 dBm at 20 kilohertz. 50 kilohertz separation on the unit with the pre-selector, and I have set about a 3 dB loss. I turn off that strong signal. So it's about 3 dB. It's hard to do this very accurately. It takes too much time. And the signal level I see now is -22 dBm. And I switch that off and switch this one on. And signal to noise ratio seems a little bit better. So I increase 1 dB. And then I remove this strong. And there's a little bit more than 3 dB loss, so I shouldn't have added that 1 dB. Which means I have the same, -22 dBm. Still at 50 kilohertz, I go to this one. And I think it has drifted a little bit. Wrong direction. I want to keep it at the center of this filter here. And I switch off the strong signal. And we have the same results. So -22 dBm at 50 kilohertz. So this is the 1633 without the strong signal, and now I enable it. And degradation is 2.5 dB. So I increased the interference by 1 single dB, and as a result sensitivity is lost and I lose more than 4 dB. So I go back that 1 dB and there is no improvement. Means this is no longer reciprocal mixing. This is the effect of the AGC, the RF AGC of the 1.2.0 firmware. So I have to switch it off and then on again to restore the loss I had before. And this happens at the level of minus 19 dBm. Now, this unit does not use AGC. I make sure that I clear the memory effects that it might have by doing that while having no signal, no strong signal present. And then I add the signal 100 kilohertz below in frequency. And I look here, the loss is 1, 2, it's a little more than 3 dB. Maybe let's step off 1 dB like that. Now it's 3 dB. And I read minus 19 dBm. And now the unit with the preselector, I have the strong signal present and I switch it off. And it's something like 3 dB. I don't want to wait for accurate readings. The level I have here is minus 18. Now the signal is 0.5 megahertz below. I'm running the 1633 and I have a modest degradation, as I can show by switching off that strong signal. It is about 1 dB. So I put the strong signal back. The level is minus 19 dBm and I increase by 1 dB. As you can see, I am losing 2 dB of signal to noise ratio and I have more than 3 dB loss. So I turn it back 1 dB. And of course, I don't get performance back because I have triggered the AGC and there is some hysteresis there. So I have to make the signal a bit weaker to make the AGC shift its state. That means that the level I note for the 1633 is minus 19 dBm. So here is the one without HF AGC and without preselector. this is the signal to noise ratio, and I switch on the strong signal, 0.5 megahertz away. And it makes no difference, almost no difference. And the level is minus 12 dBm. And then I increase by a single dB and lose performance completely because I brought it into saturation at minus 11 dBm. So minus 12 is the limit. The unit with the preselector is very similar. I have it now at minus 11, and then I add a single dB, and then it saturates. I go back that single dB to restore the performance. So there is a 1 dB difference, not much. The 1633 SDR sharp, I have a 3 dB sensitivity loss. It is due to the HF AGC, and I increase the level 1 more dB, and that's the threshold for the next step on the AGC function. So I go back 1 dB, and still the result is not so interesting. So I switch the LED signal off and then on again to get back to this about 3 dB loss. And that happens at the signal level of minus 11 dBm. Here is the unit without the preselector. The signal level is minus 10 dBm, and the loss of sensitivity is about 2 dB. So I increase by a single dB, and performance goes down dramatically. And I go back that single dB, and then come back to the same situation. So the unit saturates at this level, minus 10 dBm. The unit with the preselector at a level of minus 7 dBm, the signal to noise degradation is very small, and I add 1 dB and it goes into saturation. So I note this as minus 7. I have now placed this interference 6 megahertz down. That is on the medium wave band where signals could sometimes be very strong. And then looking at the 1633 SDR sharp software with the 1.2 firmware, and I have about 3 dB loss, and the signal level is minus 12 dBm, and I add 1 dB, and that's okay. Well, one more. That's not okay. And then I go back 1 dB, and this means I hit the AGC threshold, and that was at the level of minus 11 dBm. Not surprising, it's the same level as I had at 5 megahertz. The 1.7.0 firmware with the 1672 SDR sharp looks like this at minus 11, and I give it minus 10 dBm, and some things goes very wrong. I get overtones from that 1.6 megahertz. The unit with the preselector is different now. The signal level, it saturates the perceives. I have to enable the 10 dB attenuator to be able to get the signal level. It's plus 2 dBm, but there is no degradation. And this is the maximum signal level I can get with this current setup. I think this is not, it just shows something. There is a preselector and it stops the medium wave bands. It's more interesting to look at the intermodulation problems due to several signals at much lower frequencies. So I will not try to bring up the level here. Well, there was an easy way of bringing up the signal level. I reduced the attenuation in front of this unit by 10 dB nominally. Looks like 9 dB here. So the signal to noise ratio is 9 dB higher, and then the signal is also 9 dB higher. And I switch on that medium wave, which is now 9 dB above those plus 2 dBm I was reading, means plus 11. And as you see, it doesn't affect signal to noise ratio. So here are the results. At very close range, there is some noise in the perceives, noise on the sideband noise on the sampling clock. But on the HF Plus, that noise is pretty low. So the difference from the perceives to the HF Plus units is only 8 dB. And it's the same on both sides, roughly. Now, at 5 kHz separation, the HF Plus is about the same, but the perceives is 5 dB better. At 20 kHz, there is a noise hump in the HF Plus, because that is a typical characteristic of the PLL that's used for the local oscillator, while the perceives has reached its flat noise floor. So the difference at 20 kHz is 20 decibels. And then at larger separations, the HF Plus becomes a little better. And then at very large separations and with the preselector, the HF Plus is above plus 11 dBm. The perceives also has a preselector, and it's probably similar, and I haven't measured that because I cannot give the perceives enough signal. This will be not very interesting, so I will not try to do this kind of measurements, but I will see something which is far more important, and that is the effect of several signals on half the frequency or much lower frequencies, how they intermodulate and create interference. And that's another video. The noise floor is at minus 121 dBm in 2 kHz bandwidth. This means that the noise floor would be minus 154 in 1 Hz, which means that the noise figure is 20 decibels. That's for the perceives, and I have set the noise figure of the other radios to the same value as you can see in the introduction video that I referred to in the beginning of this one. That means that the noise in 500 Hz is minus 127 dBm, which means that the dynamic range at 20 kilohertz separation is 103 dB. That's the worst point where the phase noise has hits maximum. And then at 100 kilohertz, the dynamic range is 108 dB. And very close, the dynamic range is also a bit better than 103. And then what happens when the preselector is introduced, it's another story, I think. I just wanted to show that it really is there and it makes some effect.